Hello. In this video, we will talk about the Bayes rule again, and this time we will use two-way discrete table to explain the Bayes rule and show a case study of disease diagnosis. So first, the Bayes rule we have talked several times in our videos. So this formula is to take the relationship between the prior and the posterior probability. So here we can see the PC is the prior, and the PRC or PC given R conditional probability is the posterior. So what this means? This means if we have no information about R, so both C and R have related and R is the result, and we only get the population's probability, so we only know probability C. This is a prior probability, a general representation of the population of this probability. But now we get additional information such probability that the case or event R occurred, and we also has information such conditional probability of R given C. So in numerator is probability PC, PCR both occurred. So PCR both occurred equals equals PC times PR given C. So this case, this is the same as PCR, both in the parentheses. So PCR divided by PR, this is the conditional probability of PC given R, right? So if we look at the denominator PR, we can also write as a total probability of PR for each case, separated in each case of C. So here PC asterisk means for each kind of C. So in the numerator is only one kind of C. But PC asterisk, which means the different values of PC, then times its conditional probability of R given its corresponding C. Then this probability multiplication take together summation for all the C case. So we go to a two-way categorical table, then will make you understand better for Bayes rule with the relationship as the marginal probability and conditional probability. So this table, we has row and column. So row is the R. We can see this is actually the result in the previous page, and C is the PC. For the column C, PC is the prior probability. So for this column marginal, this is the marginal probability. This C is the prior probability. So which means if we have no other information, we just take randomly from population, we can only know this probability of C. Then now we have information in this table. This table actually each field is the probability of RC, right? But this RC, probability RC can be written as the multiplication of PC times a conditional probability of PR given C. So here C is for the specific value of C, but this C is for these specific values marginal probability. So for the row is also marginal, right? For the row is also marginal. So this row, for example, PR represents the probability of R, and this actually is the denominator of the previous page's Bayes formula. So for this PR, we can write as a total probability expression. So which means using each value of C asterisk in this row times the conditional probability in this row. So which means the Bayes formula says if we have no information of R, we can only know the prior probability. This is the marginal. But if we know the conditional probability, so we can get the posterior only from this row's information, because this is the denominator of Bayes formula, and we use a particular field in this row, then divided by this marginal. So we get a conditional probability, which is the posterior probability. So we can say the Bayes rule is going from marginal to conditional probability. So if we look back, so this PC is the prior, and this is the marginal, and this is the conditional. So PC is the prior, is also a marginal. So we update our credibility of probability C from a prior or a marginal to a conditional probability. So next we show a case study similarly using such kind of table. So we consider trying to diagnose a rare disease. So this disease is very rare. Suppose that in a general population, the probability of having the disease is only 1 in 1,000. So which means generally, if we take a person, what's the probability that he or she has the disease? We can generally use prior probability 0.001. So we denote the true presence or absence of the disease as the value of parameter theta. So theta, which means if theta has this symbol, which means the disease is present in the person. And if the theta is this smile symbol, means the disease is absent, no disease. So we know the base rate of the disease can be denoted as the probability of theta equals this Z symbol is 0.001. So this is our prior belief that a person, if selected randomly from the population, and we can only say this person has 0.001. Just like we have no other detailed information, but we select a person from population, we know maybe he or she has the cancer or skin cancer 0.001 probability, right? So this is the prior probability. And for this kind of study, for diagnosis, has a hit rate. So what 99% of the hit rate. So what means hit rate? So hit rate is that if the person has disease, actually has disease, and the test result is positive 99% of the time. If this person has this disease, and we can get the result, test result 99% of the time is positive. So we denote the test result positive is T equals plus symbol, addition symbol. And the negative test result can be denoted as T equals the negative. And the opposite of the test result in the data that we'll use to modify our belief about the value of the underlying disease parameter. And the hit rate is expressed as the conditional probability if this person has this disease and the test result is positive. So this is the conditional probability of test result positive given this person has disease. So this probability is 0.99. Also, we have another rate called false rate, alarm rate. false alarm rate means if this person has no this disease, but the test result is positive, and this kind of conditional probability is 0.05. So this means the false alarm, because this person has no disease, but the test is positive. So now suppose we sample a person at random from the population and take the test, and the test result is positive. So the question is, what is the posterior probability that this person actually has the disease? So we want to calculate the posterior probability of this person has disease after we get the positive test rate of this person. So if we use mathematical expression, this is to calculate the probability of a conditional probability of this person has the disease given the test is positive, right? So before we using Bayes' rule to calculate this case study, so what is the intuitive answer for you? And maybe many people will think that the person maybe has about 99% or very close to 99% that this person has this disease, right? Because the 99% of the case, if somebody has disease, will be positive, right? So now positive, and this person maybe 99% has the disease. But actually, is this correct? So we will use this table to apply Bayes analysis. So in this table, for left side, we have test positive and negative. And for the column disease, we have has disease and no disease, right? So this is a two-way categorical table or contingency table. And for disease, because we now will calculate the conditional probability of disease is positive, has disease, given the test is positive. So we want to calculate between, for this case, right? So if this person gets the positive test result, what is the probability of he has disease, right? So we can see the marginal probability first. This marginal is the if from the table before we know this marginal probability is like the prior probability. So if we have this kind of information, the disease proportion in the population is 0.001, and about 99.99% of the people has no disease, right? So this is 0.001 and this is 0.999 for the marginal probability of disease proportion. Then we have to fill each field in this table. So you can see for both the person has disease and has positive test results is the person prior probability 0.001. Person generally has this disease times the probability of positive test result given the person has disease. So this is 0.001 times 0.99. This is the hit rate, right? And if the person generally has 0.001, then if the test result is negative, there's 1 minus 0.99. So this is the complement of the hit rate. So if this person has disease, and 99% of the case, it will be tested positive. So which means 1% of the case, the test will be negative, right? So we multiply this together, prior probability of disease times conditional probability of negative test result given this person has disease, then we will get this part for this field, which means the person has disease but test is negative, right? And similarly, we can calculate the field for the person has no disease. So generally, the person has no disease, the probability is 1 minus 0.001. And if the person has no disease, but the test result is positive, what's the probability of both cases will occur? So we multiply the prior probability of this person has no disease, but the test result is positive. So this is a conditional probability of a positive test result given the person has no disease. This is the false alarm rate in the problem, 0.005, right? So times together. And similarly, we feel in the last field is the person has no disease and the test result is negative. This is the prior probability of this person has no disease times the conditional probability of negative given this person has no disease. And this probability actually is 1 minus 0.05. So we fill all 4 fields and we can calculate the marginal for these 2, right? And next, we can calculate the probability of the person actually has disease given the test result is positive. So for this field, just we consider this marginal and calculate the conditional probability of this field divided by this marginal summation, right? So this means from marginal to conditional, because from the marginal is prior generally is 0.001 for a person have disease. Then now we get from Bayes formula we get the conditional probability, and this is the posterior probability, which equals this multiplication divided by this total probability. So this is a conditional probability from marginal to conditional. So if we look at this calculation, the probability of the person has disease given the test is positive equals the probability prior times this conditional. So this is actually the field probability divided by total probability of this marginal. And this marginal is 2 case summation. So one is the person has disease and tested positive. Another case is the person has no disease, tested positive. So the result is only 0.019. So which is although the prior probability of a person has disease is 0.001 and the hit rate of the person has disease and the test result is positive is 0.99. But now we get a person tested positive, but actually this person's probability of having a disease is only about 2%. So which means this test method is not so strong to say the person has disease or not, right? Because only 2% of the chance if the test is positive, this person has disease. But why get it so bad result? Because if we look at this formula, because there is only 0.1% of the people in the prior, which means 99.99% of the people having no disease. So this is a very rare disease. And second, there is relatively very large false alarm rate for the test, 0.05. So which means this part is significantly larger than this part, right? So which means the result will be very small because this part is about 40 to 50 times larger than this one, right? So if we think again, so positive, get the test result positive can have two cases. One is the person has disease, then test positive. Another is the case the person has no disease, can also get the positive result, right? But this second case represents the most of the people. But the first case is only very small, right? Only one person in 1,000 person, right? So which get the result of the test result of the person actually has disease and tested positive is very low, only about 2%. Now, thanks for watching our videos for Bayes analysis, and we have also website for Python and R training and many cases for the statistics problem. Thanks for watching.